Good morning, everyone. Imagine an insect that spends 17 years underground in total darkness, then emerges by the billions in a synchronized spectacle that transforms entire forests. That's the periodical cicada, and the numbers behind its life cycle, 13 and 17, are not random. They're prime numbers. Today, I'm going to convince you that this is one of the most beautiful marriages of mathematics and biology ever discovered, but also that the story is more complex and more fascinating than the textbook version suggests. Let's dive in. Here's our roadmap. First, we'll meet the insect itself, the periodical cicada. Then we'll unpack the mathematical logic of why prime-numbered cycles are so hard for predators to sync with. We'll look at the hard evidence, computer models, field data, staggering population densities. But I also want to take you into the controversy, because not everyone agrees the prime number story is the whole truth. Finally, we'll step back and ask what this teaches us about evolution as a kind of algorithmic problem solver. 5 acts. Let's begin with the phenomenon. Let's start with what we're actually talking about. When people say cicada, most picture the annual green cicadas of late summer. Periodical cicadas are different. They belong to the genus Cicada, found only in the eastern United States, and they spend either 13 or 17 years underground as nymphs before emerging all at once. Not 12, not 14, not 16. Always prime numbers, and when they emerge, they don't trickle out, they erupt. The sound can reach 100 decibels. Entire regions are transformed. This isn't just a quirky fact, it's an evolutionary strategy that has been refined over millions of years. Here's something that often gets lost. Out of the hundreds of cicada species worldwide, only 7, all in the genus Cicada, have these prime-numbered periodical life cycles. 3 species run on a 17-year clock, 4 on a 13-year clock. Every other cicada on Earth emerges annually or irregularly. So the question isn't why do cicadas use prime numbers, it's why did this one small group evolve such an extreme strategy? The geography matters too. The 17-year cicadas dominate the cooler northern states. The 13-year ones thrive in the warmer South and Midwest. Temperature may hold part of the answer, which we'll come back to. Look at that number. 1.5 million cicadas per acre. Let that sink in. In a single brood's range, we're talking billions, possibly trillions, of individuals surfacing within a few weeks. This is the other half of the strategy. Prime-numbered cycles keep predators from synchronizing, but mass emergence ensures that even if every bird, mammal, and predatory insect in the area eats itself into a coma, they can't possibly consume more than a fraction of the population. It's predator satiation on a scale that's almost hard to comprehend. The survivors, and most do survive, have a clear path to mate and lay eggs. The math protects the cycle. The crowd protects the individual. Now let's get to the core mathematical argument. Suppose a predator has a 3-year population boom cycle. If cicadas emerged every 12 years, that predator would hit them every single time. 12 divides perfectly by 3. But 13. After 13 years, the predator has gone through 4 full cycles plus 1 extra year. The predator is out of phase. After 17 years, it's 5 cycles plus 2. The cicadas always emerge when some portion of their predators are at a population trough, sexually immature, fewer in number, less capable of exploiting the feast. Prime numbers, by definition, share no divisors with smaller numbers except 1. This means no short-cycle predator can ever fully synchronize. It's a mathematical lock. Let's make this concrete. On the left, non-prime cycles. If cicadas emerged every 10 years, any predator on a 2-year or 5-year cycle gets a guaranteed feast every time. 12 years? Even worse. It aligns with 2, 3, 4, and 6-year cycles. A predator buffet. On the right, prime cycles, 13 and 17, share factors with nothing except 1. The only predator that could sync would need its own 13 or 17-year cycle, and that's extraordinarily unlikely to evolve independently. Mathematician Glenn Webb tested this with simulation models. Non-prime populations were, in his words, annihilated or significantly reduced. The primes survived. The math isn't just elegant in theory, it works in silico. Take a look at this chart, which illustrates what Glenn Webb's population model found. The non-prime cycles, 10, 12, 15 years, show survival rates that crash toward 0. predators lock on and the population gets hammered generation after generation. But 13 and 17? Survival rates above 90%. These aren't real field measurements. Webb built these from mathematical population dynamics equations that factor in predator cycles of 2 and 3 years, nymph survival rates, and fecundity. The model is clear. Prime-numbered emergence is not a marginal advantage. It's the difference between persistence and extinction. This is evolution doing mathematics without a calculator. But here's where the story gets really interesting. The prime number predator avoidance hypothesis is elegant, satisfying, and taught in textbooks. But is it the whole truth? A growing body of research suggests the real driver might have been climate, specifically the Pleistocene ice ages. Let me take you into the debate, because this is science at its best. A beautiful theory meeting stubborn facts that refuse to fully cooperate. Researchers from Brazil's Universidade Estadual de Campinas ran computer simulations similar to Conway's Game of Life and found that prime-numbered cicadas did indeed have the best evolutionary strategy against predators. So far, so good. But Lou Sorkin, the American Museum of Natural History's cicada expert, points out a timing problem. Cicadas evolved during the Pleistocene, when glaciers advanced and temperatures plunged. A 2023 paper in Scientific Reports built a model showing that glacial cooling, not predator avoidance, likely drove the initial switch from size-dependent maturation to period-dependent maturation. In this view, the prime numbers came later, a secondary refinement, not the original cause. This quote captures both the power and the limitation of the hypothesis. Yes, the computer models confirm that prime cycles outperform non-prime cycles. Given the rules of the simulation, 13 and 17 emerge as the winners. But a simulation is only as good as its assumptions. If the real evolutionary pressure was glacial cooling rather than predator synchrony, then the model is answering the wrong question. This is what makes the cicada story so rich. It's not a settled case. It's an active area of research where mathematics, paleoclimatology, entomology, and evolutionary biology are all in conversation. Let's trace how the scientific conversation has evolved. In 1977, Stephen Jay Gould, in his essay collection Ever Since Darwin, gave the prime number hypothesis its first major popular platform. It was elegant, intuitive, and it stuck. In 2001, Glenn Webb put mathematical rigor behind it, building population models that showed non-prime cycles leading to annihilation. In the 2010s, the Brazilian team's cellular automaton simulations gave it computational support. But in the 2020s, the tide began to shift. New models incorporating Pleistocene climate data suggested temperature, not predation, as the primary driver. Science doesn't always move in straight lines. Sometimes it spirals, like a cicada's life cycle. So where does this leave us? The cicada doesn't know what a prime number is. It doesn't do arithmetic. But through millions of years of variation and selection, its lineage stumbled upon a strategy that turns out to be mathematically optimal, whether against predators, climate, or both. That's the deeper message here. Evolution is an algorithmic process. It discovers solutions to problems that we, with all our mathematics, are still working to fully understand. The periodical cicada, with its 13 and 17-year rhythms, is a living proof that nature has been running sophisticated computations long before we showed up with our equations. Thank you.